Okay, so we're thinking of a transformation of the line element for space. Now this represents an infinitesimally small distance in space. Let's say that we start where we ended off in the previous lecture with the line element in r and theta coordinates. So that's what the line element looks like. And we want to get this in terms of x and y. And so what we want to do is transform from r and theta to x and y, and r is equal to x squared plus y squared to the 1/2, and theta is the inverse tangent of y over x. So in terms of these little differentials, right, we need dr and we need d theta, and we're going to square them. So dr, so we're going to use the chain rule to relate dr to its x and y functions. So we're going to take the derivative of r with respect to x, dx, plus the derivative of r with respect to y in dy, and we'll get the differential in terms of x and y. So we have to do these operations. So the derivative of r with respect to x is similar to the derivative of r with respect to y, except that we'll have a y in the numerator for this one and an x in the numerator for this one. So it looks like x over x squared plus y squared to the 1/2, and then we have the dx, and here we have the same but with y over x squared plus y squared to the 1/2 in dy, or times dy. And so now we can do dr squared, and that is, right, so it's this whole thing squared. That's going to give us x squared over x squared plus y squared dx squared. And we'll square this term and then take the cross product, plus, or the cross term rather, we should say, y squared over x squared plus y squared dy squared, plus twice xy over x squared plus y squared dx times dy. Okay, and now we need to go to the d theta, and then we'll square that. So d theta is equal to d theta by the chain rule. Its dependence on x, d theta by dx times dx, plus d theta by dy dy. And that's a little less obvious. The derivative of the inverse tangent is 1 over 1 plus the quantity squared. Squared, and then we have, so it's going to look like it's going to look like 1 over 1 plus the quantity, which, well, if we're doing it with respect to x, then y is a constant, and so it's really in y over x quantity, so we get a y over x squared, and we're taking derivative with respect to x, so we have 1 over x here becomes a minus 1 over x squared, so we have a minus y over x squared here, and this is in dx, or times dx rather, plus a similar thing, except we're going to now take a derivative with respect to y, so we have that squared, and when we take the derivative with respect to y of y over x, we just get 1 over x, so that's 1 over x here, and then we multiply by the differential dy, and that's d theta in x and y coordinates. And so d theta squared looks like we have to square this, so we get y squared over x to the fourth divided by this squared, 1 plus y over x squared dx squared plus this one, 1 over x squared over 1 plus y over x squared, all of that squared, times dy squared, plus the two terms that we get by multiplying these two. So there's a minus sign, so we get minus 2 y over x cubed. So this is a y over x cubed divided by 1 plus y over x squared. And this, of course, is going to be squared. And we have dx dy. And so this looks like, let's see, we can simplify this. We can find the denominator is the same here, so we're going to add these three. Let's see. I can pull out. I can make this. I can pull these x and put these x's back into here and make this x squared plus y squared. So this becomes y squared. Right, that's dividing by x to the fourth. So that looks like 1 over x squared plus y squared dx squared plus x squared over x squared plus y squared dy squared minus twice xy over x squared plus y squared dx dy. And so we have dr squared here. So we need, let's point out that this is our dr squared, and we're going to add to that an r squared d theta squared. An r squared d theta squared. So I have to multiply this by r squared, and r squared is just x squared plus y squared, r squared plus x squared plus y squared. And so we can get rid of one factor of x squared plus y squared. And so r squared d theta squared looks like y squared over x squared plus y squared dx squared plus x squared over x squared plus y squared dy squared minus 2yx over x squared plus y squared dx dy. And we can now add these together and do dr squared plus r squared d theta squared is equal to, so we're going to add this object, this thing to this thing, and so the dx squared has in front of it, notice that we have this added to this, and that's x squared plus y squared over x squared plus y squared. So that's just dx squared. then we have this, and that's again the same thing, x squared plus y squared over x squared plus y squared. That's 1, so we just have dy squared. And then, as we expect, we're adding this to this, and they're just equal and opposite. And so there's no cross term. And so we showed how to transform from the spatial line element, the differential line element, in terms of r and theta coordinates, into one that involves x and y coordinates. And so we can see that with this transformation, our metric becomes the one that represents a flat space. And in these other coordinates, r and theta, we have 1, r squared, 0, and 0. Perhaps it wasn't obvious that that was a flat space, but the point is that we can do this transformation and show that the metric can be placed into this form, indicating that we're dealing with a flat space. And so we're going to move to a curved space and see where this becomes impossible. We won't be able to find a transformation that will make the metric everywhere look like that for space, and then these ideas will transform or translate directly into our analysis of space-time.